about a dork professor. Well, not about a dork professor, but about a class she was taking at dork. I think you might still have it. I should read that to you. Just because, you know, you might actually go to dork and you could know who this guy is. And it'd be kind of funny. This is what she said. Now, granted, she probably was a C student in advanced chemistry. Okay. Said they wanted to put me in Chem 101, but I tested out, and now I'm in Chem 111. The books they're using for the class are the same ones we used in your chemistry class. First, we got into polyatomic ions in both biology and chemistry, and I've been using your polyatomic ion list nonstop. In chemistry, we're also doing a lot of stoichiometry, and I've been using your conversion bridge nonstop. It's been saving my life. When balancing chemical equations, I showed people how you showed us to do it and write it out, and now the whole class is doing it. And I showed it to Dr. Weischer, and he showed it on the board to the whole class after he saw us using it.
Isn't that a normal way of doing it, though?
Yeah.
I guess. I didn't think my way was any unique. I got it from somebody. And your Vesper cheat sheet. I don't know if you guys remember that one. It's the molecular geometry cheat sheet that has electron concentrations, number of regions bonded, and what the geometric shape is, tetrahedral, trigonal, planar, all that.
Type has lane.
Yes.
Type has lane.
She says. And your Vesper cheat sheet has been sweeping the nation. My teacher made copies of your sheet and handed them out to the class as a guide.
Kramer, college professor.
Right, so I mean, if it went there, we could probably do pretty well.
And he said that hopefully after referring to it for a while, we'd have it down. Thank you for all that you did. It's like, okay.
I mean, I had a coworker. She passed advanced chem, and then she was at their school did AP chem, apparently they were different. She couldn't tell me the charge of sulfate once, so I don't know how good South
Bravo, you guys will be prepared for college.
I mean,
Okay.
so-
Yeah, Kara came in and told me she tested out a first year college chemistry. She clubbed out of it.
you still pay the same amount, you know?
That's what the class is hard.
Really?
Yeah.
Iowa State's known for having a really tough.
Just go to UNI.
Oh, I don't know.
I think she said it new because they do so many labs for like
We can't-
That's one thing I don't prepare you much for.
We can't-
I hated lab reports. Lab reports awful.
Well, our school doesn't have money for that.
Or the time. I know a lot of public schools. They like start 3 weeks earlier in advanced chemistry, or like AP chemistry. Like the kids come in like for 3 hours during the summer each day.
That would not be fun.
Because,
I do it.
well, to get
Prepared.
enough ahead that they can do labs through the year. Because to be AP, you have to like do so many labs. Well, a college lab is a 3-hour window.
Yeah.
Like, if you take any science class, you'll have your regular hour class 3 days a week, and then you'll have another day where you'll have a 3-hour lab. And so you're talking about 6 hours. That's why I always thought that people who were in science majors got completely just ripped for credit hours, because you take 6 hours and you only get 4 credits. Versus if you take 6 hours of any other classes, you get 6 credits. Yeah, because the lab's only worth 1 credit, even though it's a 3-hour commitment. So I think it's a complete joke. Not to mention you pay 5 times the amount for your books.
But you get
Because you get books like this that are huge. This would be like, if you were getting it from the bookstore, it'd be like a $150 book. Versus like, you take a Bible class or you take a history class, you get this little like, yeah, like $25 book or whatever. I would average like $700 a year for books. And you get what, 200 back, maybe 130 back.
That's why
When you sell them back.
on Amazon, if you can buy used ones, or you can even rent used ones. Like,
Sure.
my psychology book.
Yeah,
Renting it for
things
like
have changed a little bit
$45.
since when I was in college, for sure. All right, so
Yeah, it's mailed back by December 28th or something. Getting close, but-
so is she taking first year chemistry? Anyone that?
I think so, yeah. I think she said it's pretty, like the class is like probably about this level, but then the labs are really hard. Like the tests take like the full class time and lab tests take 3 hours.
Nice.
Yeah.
It's kind of what you guys take your test. Good. Yeah, right where I need to be. Perfect. All right. So here's what we're going to talk about today: is standard enthalpy of formation. Okay. We used this equation last year quite often. You guys remember the products minus reactants equation that we did last year, where we just looked in the back of the book and we got numbers and we plugged them in, and we really didn't know what we were doing, right? We just plugged and chugged because that's what we were told to do. Right. Okay? Can I show you where all this stuff comes from? Just because I used to just do the plugging and chugging and be like, what in the world is this for? No, it wouldn't. Grant! You're supposed to say yes to make me feel like you want to know this stuff. Okay? So here's what we're going to do. First of all, this degree symbol means standard state. Have we talked about standard state? Oh, there it is. What's the difference between standard state and STP?
Standard state, that means that it's path dependent, just final mass initial. Isn't that's state function? Never
Yeah.
mind.
What's the difference between STP and standard state? Well, if you
it's-
knew what STP was, what is STP? Okay, but what is the standard temperature and pressure? What is that in Celsius? 0. What's the difference?
25 degrees.
Temperature's different. Okay, it would make sense why the standard temperature for doing heat problems would be approximately room temperature and not freezing.
Yeah.
Make sense? Okay? This little F means formation. What's really cool about this is they came up with a standard situation and said, we can compare how much energy will either be lost or gained in the formation of all of these different chemicals. So if you pull open your book, there is a table somewhere. Actually, it's probably in the way back. Get to the way back. In the blue section, I would think. There it is, Appendix A20, approximately.
The 19 through 21, 22.
Just go to A20, enough to prove my point here. Okay, so you can see those are all the enthalpy of formations. What's interesting is most of those guys are what, from a science standpoint?
Negative?
Negative. Okay? And it has to do with what they set as their standard. So their standard is, if you remember, any elements in their natural state or any elements by themselves are considered in their standard state and have no enthalpy of formation. So a lithium atom by itself, enthalpy of formation would be
0.
0. It naturally occurs as lithium. That's where it's naturally going to be. Okay? Hydrogen gas. What do you think that's? What do you think that enthalpy of formation is?
0.
0. What about oxygen gas?
0.
Same thing. Okay? But remember, things bond for a purpose. Typically, why do things bond? To become stable, which means what from an energy standpoint?
Lost energy.
Low energy. Okay? Well, wouldn't that mean a negative enthalpy would be a loss of energy? Okay, so you can see that forming just random compounds from their standard conditions or from their lone elements is usually a favorable reaction, isn't it? Okay? Now, where do we get positive change in H then? Well, it comes from, okay, it's an endothermic reaction. Well, remember, normally when we do a chemical reaction, we don't start with individual atoms, we start with other compounds, right? Well, if your reactants are actually more stable than your products, your change in H is probably going to be positive, right? But if it's the other way around, it'll be negative. Okay, let me show you what I mean here. Do you have a spot in your notes too? Did I give you a nice big old blank? Tell me I gave you a nice big old blank. I didn't give you a single big old blank. Crud. All right. Not the part that has the problem. So yeah, if you can find space to put it here, do it. But otherwise, it's just for your fulfilling enjoyment. Okay. So we are going to look at this. Methane reacting with oxygen gas. And we are actually going to use Hess's law here. We're going to use the enthalpy of formation stuff in this context. So I'm over here going to kind of break it down into what's really happening. We've got your reactants.
That problem's not in the notes, right?
What?
That problem's not in the notes. Yeah. Okay.
Every chemical process, every chemical reaction undergoes this process. Okay, so when you have a chemical reaction, what happens to the reactants? How does it get to the products? What goes on? You guys know? Every single chemical reaction goes through the same type of process.
Oh, intermediate steps, or
No, I'm not worried about that. I'm just talking about how do the reactants get to the products? Don't overthink this. This is not a deep question. What do the reactants have to do in order to become the products?
Bond.
Okay, yes.
Activation has to be
We'll say that's A. We'll get to that in a sec. We'll say that's going to be B. In order for the reactants to go to products, the reactants have to break apart.
Oh. Yeah.
So this is going to break apart into carbon, that's solid. So that is going to break apart into H2. This guy doesn't need to break apart. So this is step C. We'll get to that here in a sec.
How do you know that carbon is solid?
Because it said so. I don't know. Okay, so here's every chemical process starts this way. You got your reactants have to be broken down, your elements that you have rearranged, and then form new what? What? Yeah, right. So your reactants bonds have to break, the elements rearrange and form new bonds to form new products or new compounds. So I would say the carbon from here is going to go to produce that. Hydrogen's going to go to produce that, and oxygen is going to be used in two spots. There and there. And I'm just kind of drawing all over the place here. Okay, so we're actually going to apply Hess's law here. Let's start with the very first thing for A. Okay, we know that this guy has to do what in order to ever become a product? It has to what? Break down, break apart. Okay, this has a change in H of 75 kilojoules per mole. Now, can I flip that reaction?
Yeah.
And what would it do to the enthalpy? Okay? Let's do B. What does that mean? Yep, change in H is 0. Okay, here are your reactants.
So just H or O2.
Yeah, just okay. Okay, then we got our products. What's the matter? You know where to write all this?
Yeah, I think.
I think it right next to the home, right there.
No, I know.
Okay. So then we know that we said to form CO2, what produces the CO2?
CH4.
No, what elements?
Oh, carbon.
Carbon as a solid plus what else? O produces CO2, which I'm probably going to need to. Why did I put 2 there? Okay. Okay, this is forming CO2 from standard conditions. These would be 0, 0. This would be just the formation value that we can find in the back of our book. So that number is this. Okay? D. What plus what gives me H2O?
Hydrogen.
And again, 2 standard states forming a particular product. This will be a formation here. It's negative 286 kilojoules. Now I need to take that and I need to multiply it by 2 because it forms 2 moles of H2O.
Negative 572.
Okay? Now, really I've got A and B is the breakdown of my reactants, and C and D is the production of my products, and I know the enthalpies of every step, can't we just use Hess's law?
Yeah.
Would be the sum of all of them. 75 plus 0, correct?
Yeah.
I don't know why I put parentheses around all this. Plus negative, or did you want me to just do negative? Minus 394 minus 572. What does that give us?
Negative 891.
So what we found is, would you say the reactants or the products are more chemically stable based on that answer?
Products.
Products.
They're much lower.
Much lower energy. Yep. And so this is a very, very vigorous reaction typically. Methane with oxygen gas, that's pretty reactive.
Really?
You need a spark. As soon as you got the spark,
Explodes, yeah.
yeah. Okay? And we'll talk about that, where that comes into play much later next semester. Okay? Now I wanted to show you something. Okay? This was the breaking down of something. This would have been 2, but it was in its standard state. And these were the formations of things, correct? Let me show you how this works from our equation that we've been doing. We have the formation value numbers of my products minus the formation value numbers of my reactants. Why is that there?
Because it's always final minus initial.
That doesn't explain it. You're just saying that's what the equation says it is. I want to know what in the context of what we do here for every chemical reaction, why is that negative? Okay, I can understand that. Remember, I'm using the formation values of both. Does that help you? Are we forming reactants? What are we doing with our reactants? Which would be the opposite of forming, right? Everybody see this? We could do all of this, apply Hess's law, and find that answer. Or we could use this equation because we know that every chemical reaction, your products are formed, so we use the formation values that the book gives us, and we just do the opposite of the formation values of the reactants, because if I go forward one direction and I flip it, it's the opposite sign in the other direction, correct? So technically, my enthalpy of formation for this, if I was forming that, is actually negative 75 kilojoules per mole. But when I'm breaking it down, a minus a negative would give me the number I want. You see, if I plugged in the formation value into this, it would give me that number. Everyone see it? Because I'm subtracting a negative, which would make it a positive. Okay? So now we can just go and do this really easily. We can find the change in H of the reaction by plugging in all the formation numbers, products minus reactants. Those are my two products. It would be negative 394. These numbers you would get in the back of the book.
So on the test it would give it to us.
Yep. I'm gonna get rid of this so I have room. Okay, negative 394 plus a negative, it should be, okay. go back to this equation. This is important. These matter. Because in the equation it says your formation, and then it's got like times NP and times NR. What do you think that represents? What do you think the N represents? Mole. Because these numbers are per mole, and if I got 1 mole, I'm good. Okay, so I would take this times it by 1 mole, it stays the same. But I've got 2 moles of this, and that's what we did here. So this is actually the enthalpy of formation here. So 2 times negative 280, what is it, 286. Okay, there is our products minus our reactants. Our first one would be 2 times 0, right? So that's just 0. Plus, if we actually plugged in the correct number from the formation, it would be a negative 75. That's what the back of your book would say if you found CH4. I'm going to look at it quick just to prove that I'm not making that up. It would be negative 75,
Yeah.
okay? Plus a negative 75 kilojoules per mole. And since I only have 1 mole of it, I don't have to multiply it by anything. That should give us the negative 891 kilojoules per mole without having to write all the equations out and figure out everything the long way using Hess's law. So this is Hess's law and the enthalpy of formation put together to summarize and do the whole process of a chemical reaction, figure out the energy difference a lot quicker. Okay?
What is like this?
That just means the sum of your products and the sum of your reactants. I think it's the simple sublimation or something like that.
They might give you they might give you like the equation like up there, and then they say find this, and then you go back and find the answer, and if it's 2, it's times that.
Yeah, so like your coefficient, because the numbers you find in the back of the book are just going to be kilojoules per mole. Well, I have 2 moles here, so you multiply it by 2. If I have 6 moles here, you multiply it by 6. Okay? All right, we'll finish this lesson on Friday or on Thursday. Go Homer. Happy birthday.
Which are we doing?
My birthday is Thursday.
What?
Are you gonna do
Your
those?
birthday's Thursday?
Yeah.
We're a short, easy lesson. I don't know what easy, but short.